Jai Hind everyone. So today we are in the process of continuing the unit 3, and that is the next topic of this unit, that is field effect transistor. We have already discussed about the bipolar junction transistor in the last 2 lectures. So today we are starting the next type of the transistor, that is the field effect transistor. So first of all, let us understand the difference between the field effect transistor and the bipolar junction transistor. So here, if you differentiate between the FET and the BJT, so BJT versus FET. So what is difference between the two? That is important to know before proceeding the working and construction of the various types of the field effect transistor. So bipolar junction transistor, as we have already discussed, is bipolar device. What we mean by bipolar device? Bipolar device means the device in which the current conduction takes place by 2 types of charge carrier, that is the majority charge carrier and minority charge carrier. Whereas your field effect transistor is a unipolar device. That means the current conduction takes place by single type of charge carrier, that is either the electrons or holes. Whereas in this case, both the electrons and holes are responsible for the current conduction. Second difference is your BJT is a current control device. It is a current controlled device, whereas FET is a voltage controlled device. What we mean by that, in case of current control device, if you recall the output characteristics of the bipolar junction transistor, it is between the output voltage and the output current, keeping input current constant. So here, if you recall the characteristic curve of the bipolar junction transistor, what is the output characteristics of the bipolar junction transistor? Here we can see that the current is getting constant even though you are increasing the voltage. Means the output current depends upon the input current. It is independent of the output voltage, and that is why it is called as the current control device, because the output current of the BJT depends upon the input current of the bipolar junction transistor. Whereas if we talk about the voltage control field effect transistor, it is a voltage control device. Why it is so? Because here output current is controlled by input voltage. Output current, that I'll be discussing in the subsequent lecture today only, that output current is controlled by input current. The next is BJT consisting of 3 terminals. What are those 3 terminals? That is emitter, collector and base. And also we know that emitter base junction should be forward bias and collector base junction reverse bias for the transistor amplifying action. So for that reason, the input impedance of the BJT is low. Because if you consider this is the analogy between the PN junction diode being forward biased, and we know that when we forward bias PN junction diode, in that case, your it offers you the low resistance path, and that is why the input impedance of the bipolar junction transistor is low, whereas the collector based junction is a reverse bias. And if we reverse bias the PN junction diode, this is equivalent to the PN junction diode being reverse bias. And if we reverse bias PN junction diode, we know that it offers the low very high resistance path. Ideally, it is infinite, but practically it is of the order of mega ohm. So its output impedance is high. If we talk about the field effect transistor, it is also a 3-terminal device, but in this case, these 3 terminals are source, drain, and gate. And the source to drain terminal, gate to source terminal is reverse bias, and also drain to source terminal is reverse bias. And because of this, it has high input impedance. Output impedance is high in both the cases, but in case of field effect transistor, its input impedance is high, whereas BJT input impedance is low. The next difference is, here we can see there are the 2 junctions takes place in BJT. So because of that, the current which passes through the charge carrier crosses the junction, and because of that, there the noise is more in case of the bipolar junction transistor. But in case of the field effect transistor, there is only one channel, N type or P type. So there is no junction takes place between the path of your charge carrier, and because of that reason, the noise is less. So the noise immunity is high in case of field effect transistor, and it is low in case of bipolar junction transistor. Also, the temperature stability. If we talk about the temperature stability, then we can see that in case of BJT, we have already discussed in the previous lectures that BJT is temperature sensitive device, where the 3 parameters gets affected by variation in the temperature. What are those 3 parameters? These are the beta. Beta increases with the rise in the temperature. VBE decreases by 1 millivolt per degree rise in temperature, and also the leakage current that gets doubled with every 10 degree rise in temperature. That means beta is a temperature sensitive device, whereas your field effect transistor is less temperature sensitive, but the gain of the beta, gain of the FET BJT is more in comparison to the gain of field effect transistor. And the next difference is between the BJT and FET is that the size of the BJT is more in comparison to the size of the field effect transistor. So that is why the field effect transistor number of transistors are more on a single size IC in case of field effect transistor as compared to the BJT. So these are the few differences between the field effect transistor and the bipolar junction transistor. Now coming to the various types of the field effect transistor. So field effect transistors are of 2 types. One is the junction field effect transistor, which is also termed as JFET, and next is the MOSFET. That is, MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. MOSFETs are of two types. One is the D MOSFET and second is the E MOSFET. D MOSFET means depletion type of MOSFET and E MOSFET is enhancement type of MOSFET. E MOSFET junction field effect transistor again being categorized into two categories. One is the N channel, next is the P channel. Similarly, D MOSFET are of two types, N channel and P channel. Similarly, E MOSFET are also of two types, that is N channel and P channel. So we'll be discussing all the three types of the field effect transistors one by one. So now starting with the N channel junction field effect transistor. So let us understand first of all the construction of the junction field effect transistor. So it is, in case of field effect transistor, there is an analogy between the junction field effect transistor and your normal water control mechanism. Here you can see that in case of our water system in our houses or everywhere, the tap water system, what is there? There is a tanker from where you are getting the water, and there is some bucket is, suppose some bucket is there where the water is draining, or here you can say some water is drained here, and the flow of the water is being controlled by the some knob, and that is called as the gate. So the water tank is analogous to the source of the charge carrier, and drain is the analogy, or so if you are collecting the water in some bucket, then that is the drain, and the controlling element, the knob of your tap water system, is analogous to the gate of the field effect transistor. Now let us understand the construction of the junction field effect transistor. So this is your N channel junction field effect transistor. So what is there? We consider, we take in this case, we take a N type of the substrate or N type of the material, and here the two doping of the 2p type of material has been takes place. So 2p type of materials are diffused on both sides of the N type of material, and we know that when we diffuse the or when we insert some pocket or some material in the in another type of the semiconductor material, then because of the concentration gradient, some movement of the charge carrier takes place across the two materials, and because of that a depletion layer formation takes place. So here the depletion layer formed at both the sides. Now this is the depletion region. Here you can see, now these two P type of material gets the metal contact. This is your metal contact. Metal is connected at both the sides, and these are internally connected, and we connect the one terminal to this metal contact, and that is called as the gate. On the both side of the N type of the material, we have a source terminal through a metal contact, and here also using some metal contact we have a drain terminal. So this is how we construct the any type of the junction field effect transistor. In case of N channel, P channel, we'll be taking the P type of the semiconductor material, where two N type of materials gets doped, and here you can see because of this the depletion layer formation takes place. Again, there are the two metal contacts. This will give you the gate terminal. This is source terminal, and this is drain terminal. So this is your P type of the junction field effect transistor. Now coming to the junction field effect transistors operating characteristics. So how does it work? As we know that we reverse bias the gate to source terminal and also we reverse bias the drain to source terminal, and that is why we have the input impedance high as well as the output impedance high. So initially we assume or we are keeping the VGS is equal to 0. That means we are not applying any voltage across these terminal, or we are applying 0 voltage across the gate to source terminal. So the only voltage which we are applying through the drain to source terminal. So some battery is connected here. Because this is an N-channel junction field effect transistor, so here we must have connect the positive terminal of the battery to make it reverse bias, and this is the negative terminal is connected to the source, and this is your, let's say, VDD. Similarly, here also we reverse bias the gate terminal also. So gate is p-type. So in order to reverse bias this, it will be connected to the negative terminal of the battery, and this is also, let's say, VDD. So both the potentials are same. One is at the positive potential, another at the negative potential, and that is because of that reason this will be at the 0 potential. So terminal will be at the source terminal will be at the ground potential. So initially we are keeping this VGS is equal to 0. If we are keeping VDD 0, then obviously VGS will be at the 0 potential, and now we are only changing the VDS. So here you can see this is the drain characteristics of the, this is the drain characteristics of the junction field effect transistor. Why we call it as drain characteristics, not the output characteristics? Because drain terminal is the output terminal, so it can also be termed as the drain characteristics of the field effect transistor or junction field effect transistor, to be precise. Now here we can see in order to understand this working of this junction field effect transistor, initially keeping this VGS, so effect of the VGS 0 means the effect of this VGS will be negligible on this depletion region, but due to this VDS, your region due to this VDS, I'm sorry, because of this VDS, and this is a reverse voltage. So let us understand what will be the effect of this VDS or VDS on this depletion layer formation. So here this N type of material is uniform in nature. Uniform in nature means it is having throughout the substrate or throughout the material it is having the uniform resistance. And so now as you connect, because this is N channel, so because this is N channel, so drain should be, in order to make drain reverse bias, this should be at the positive potential and source will be at the negative potential. So this VDS is reverse bias, and because of this positive potential, there are in N type of material, electron will be the majority charge carrier. Some of the minority charge carrier as also are also be present in the circuit. So here this positive terminal attract the electrons towards the junction. So electrons will be moving from source to drain terminal, so that your current will be flowing in the circuit. So gate current in case of the junction field effect transistor is 0 because of the very high input impedance, and that is why there is only one current is present, that is drain current, because drain current, if Ig is equal to 0, that means your drain current should be equal to the source current. So input and output current are same, and that is why we are having only a single current in the circuit, that is the drain current. Now, as the current is flowing in the circuit, then here if you look at this point, the here the voltage V1 will be equal to I into R. If you measure the voltage at this point, here it will be, because the resistance gets added, so here the voltage will be equal to, V2 will be equal to I into 2R. Here it will be I into 3R, or 3 times of IR, and so on. So, and last, if this is your nth resistance, then it will be N times of ID into R. So here you can see that the voltage drop here is less in comparison to the voltage drop here. Here you will be getting the maximum voltage drop, and here you will be getting the minimum voltage drop, and these voltages are nothing but the reverse voltage, because drain terminal is reverse bias. Also, you know that when we reverse bias any PN junction diode, this is again analogous to your PN junction. So when we reverse bias any PN junction diode, the depletion, what is the effect of that reverse biasing on the PN junction? It will, the reverse biasing means the depletion layer gets widen up, and that is why this depletion region gets widen up. But interestingly, this is not uniform. Why? Because the voltage drop here is less and voltage drop here is more. That means that depletion layer thickness is also non-uniform. It is an elephant-like of a structure. Means it is wherever the voltage drop is, reverse voltage drop is more, the thickness of the depletion layer is more, and where the voltage drop is less, the thickness is less. So this is how the depletion layer formation, or the increase in the depletion layer formation along with the reverse biasing of the drain to source terminal will takes place. So here I stop this lecture. I'll be continuing in the next lecture with the characteristics of the junction field effect transistor from here only. So thank you so much for this lecture, and we'll be continuing in this particular lecture. We have discussed about the difference between the BJT and FET. Also, we have discussed about the construction and the working of the field effect transistor, junction field effect transistor. Also, the effect of the reverse biasing, reverse biasing on the depletion layer width. Now, in the next lecture, we will be discussing about the characteristics of the junction field effect transistor, that is the transfer characteristics and the drain characteristics of the P channel as well as N channel junction field effect transistor. Thank you.